Okay, hello, Precalc C. October 1st, in the morning, I want to go over a homework problem from a long time ago. This is a week 2 homework problem, and okay, here we are in week 5, but you know, it's never too late. And this is a problem that I had intended to go over potentially in class, and I think even some people asked about it, but I was going to make this video and then I just never did. But I am grading some homework right now, and some people are getting this problem wrong or leaving it blank, and so I think maybe it deserves some attention. And it is a linear programming problem, and unlike sort of all the other linear programming problems I assigned, this one requires you to actually, know what you're doing and sort of think and stuff. So this is the whole point of linear programming, is to solve problems like this. So it would be a shame if we knew the math but sort of missed how to apply it, because it's a very practical kind of skill. So okay, here's this problem. I tediously rewrote the entire thing out on the board. What does it say? A farming cooperative mixes 2 brands of cattle feed. Brand X costs $25 per bag and contains 2 units of nutritional element A, 2 units of nutritional element B, and 3 units of element C. Brand Y costs $20 per bag and contains 1 unit of nutritional element A, 9 units of element B, and 3 units of element C. Find the number of bags of each brand that should be mixed to produce a mixture having a minimum cost per bag. The minimum requirements of nutrients A, B, and C are 12 units, 36 units, and 24 units respectively. Alright, there's a lot going on in this problem. Okay, where should we begin? Well, let's kind of take notes, so to speak. We have, here's a fact, brand X costs $25 per bag. That seems important. Brand Y costs $20 per bag. So maybe I even put like a box around this or something. Okay, so these 2 different brands of cattle feed have different prices per bag. Also, brand X contains a certain amount of each of the nutritional elements that we need. So 2 units of element A, 2 units of element B, this is brand X, and 3 units of element C. And then also brand Y contains, let's see, 1 unit of element A, 9 units of B. What's my color scheme here? This is getting a little bit silly. 9 units of B and 3 units of element C. Okay, and what's the overall goal? Find the number of bags of each brand that should be mixed to produce a mixture having a minimum cost per bag. Okay, so already these brands of cattle feed contain mixtures of different amounts of the various nutritional elements, and what we want to do is to find a combination of bags of these 2 different brands, which will make our cost as small as possible. So we want to find the minimum cost per bag, find the number of bags of each brand to produce minimum cost per bag. Okay, and the last thing that's really important is that we need to have, the whole reason why we're talking about these nutrients is because we need to have a certain amount of these nutrients. We need 12 units of nutrient A, 36 units of nutrient B, and 24 units of nutrient C, I guess per bag. Something like that. Yeah, okay. So, we just need to have that much. Hold on, let me just read this again. The number of bags which is a mixture containing, yeah, okay. So, good. Okay, so, let's begin. Well, I think we should summarize this information into some kind of a chart. So we really have 3 kind of things. There's like nutrient A, there is nutrient B, and there is nutrient C. And there are several things to know about these nutrients, but what I sort of care about now is how many units of each nutrient appear in each of the two different types. So if this is brand X, what we have seen is that that with brand X we get 2 units of nutrient A. So this is brand X, this is the per bag. So what I'm now listing is how many, the sort of meaning of this column is how many units of each of these 3 nutrients are contained in each bag of brand X and each bag of brand Y. Okay, so per bag of each of those mixtures, how many units of each of the nutrients am I getting? Okay, so I'm getting 2, 2, and 3. And here for brand Y, I'm getting 1, 9, and 3. Okay, and then there's sort of this kind of last column that's relevant is like, what are the minimum requirements? So how much do I sort of need of each of these nutrients? And the answer is per sort of final bag. The word bag is being thrown around a lot here, but because we're mixing bags of X and Y to produce sort of new kind of homemade mixtures, I need to have at least 12 units of nutrient A, 36 of B, and 24 of C. Okay, I'm going really slow. Hopefully you're watching this on 2 times speed. But for example, if nutrient B is found in brand Y, 9 units per bag, then if I were to use 4 bags of brand Y to make a new giant homemade bag, then that would contain sufficient amounts of nutrient B. Okay, so, alright. Well, having done all this, I haven't even just done anything yet. I'm just kind of summarizing and processing what's going on. I think we should look back again at what is the ultimate goal. The ultimate goal is right here. Find the number of bags of each brand. So, I need to, the end goal of this whole thing is I'm going to tell you, hey, mix 5 bags of brand X and 7 bags of brand Y, for example, together into a new giant homemade bag, and that's what you should do in order to minimize your costs. And minimum cost per bag, of course, because once we figure this out, we'll just keep doing this forever. Okay, so having made that clear, a good word problem skill is to pick variables to represent the thing that you ultimately want. Okay, and so let's let x, this is little x now, be the number of bags of brand X. In other words, let little x be the number of bags of brand X, which I will add to my new giant homemade bag. And let's let y be the number of bags of brand Y, which I will add to my giant homemade bag. And together, that will constitute this big homemade bag. Okay, well now, once I have variables, now I can sort of speak more fluidly about these variables. And of course, okay, it almost goes without saying that x and y have to be positive. But when I look at, when I consider the nutrients one at a time, say nutrient A, for example, well, I get 2 of nutrient A, 2 units per bag of X and 1 per bag of Y, but I need 12 altogether. So I need some sort of combination of X's and Y's such that they add up to 12. So what you now have to do is you have to say, okay, well, if every bag of X contains 2 units of nutrient A, then 2 times the number of bags of brand X will give me, will represent the number of units of nutrient A that I get by using this many bags of brand X. And then plus Y for nutrient A, I only get 1 unit per bag of Y. So this together, 2x plus y, represents the number of units of nutrient A that I get sort of as a function of the number of bags of the 2 different brands I'm using. And it's that which has to be greater than or equal to 12. So if I need at least 12 units of nutrient A, then I need sufficient numbers of the bags of brand X and brand Y such that it adds up to 12. Okay, if you get that good, if not, we have 2 more tries to understand this. Moving on to the next nutrient B, I get 2 units of nutrient B per bag of X and 9 units of nutrient B per bag of Y. So if I multiply X by 2 and Y by 9, then this 2X represents the number of units of nutrient B I get using X bags of brand X, and the 9Y represents the total units of nutrient B that I get from using 9 from using Y bags of brand Y, because I'm getting 9 per bag, so I multiply by 9, and it's that which added together has to meet the minimum threshold of 36. Okay, and then we get this 3x plus 3y, I'm getting tired of sort of talking this out, has to be greater than or equal to 24, because for nutrient C, I have X bags of nutrient X, maybe this is the easiest way of putting it. I have X bags of nutrient X, and I get 3 units of nutrient C per bag, so when I multiply, I get the number of units of nutrient C that I receive from the brand X. And then if I have Y bags of brand Y and 3 units of nutrient C per bag, then when I multiply them, I get the total contribution of nutrient C from my brand Y bags. Okay, having done all this, this was all the hard part, because I basically converted this entire word problem into a math problem. Here I have now a set of constraints, and I see that whatever my final answer is, use this many bags of brand X and this many bags of brand Y, that little x and little y must satisfy these 5 inequalities. Because if the x and y that I pick, right, find the number of bags of each brand, if it satisfies these 5 inequalities, then I can say for sure, especially these last 3, that my new homemade bag is going to contain a sufficient quantity of the 3 nutrients to meet those minimum requirements. That's actually pretty hard, I guess. Okay, if you understand all of that, then one thing we could do right now is do some algebra and graphing and all this kind of stuff, which I'm going to do in a second, to figure out the set of ordered pairs x comma y which satisfy these constraints. That's called the region of feasibility. But let me just finish my sort of reading comprehension of this word problem, because there's sort of one more important thing, which are the prices. Brand X costs $25 per bag, and brand Y costs $20 per bag. So now I can sort of create one last variable P, which sort of means, you know, my price. And okay, technically this is price per bag, but really we should call it price per like homemade bag. Well, how much when I make these giant homemade bags, how much are they going to cost? Well, since brand X costs $25 per bag, then I'm going to have to pay $25 times however many bags of brand X I choose. And $20 times Y, because each bag of brand Y costs $20. So this is going to be the total price that I pay to make one of my homemade bags, and my goal is to minimize this. So I want to find, now it's just completely a math problem, right? Find all the ordered pairs which satisfy these 5 constraints, and find the particular ordered pair which makes this P expression a minimum. Okay, now we can just kind of do the math. So here I think it's helpful to write this in y equals mx plus b form. What does it say? Y has to be greater than or equal to negative 2x plus 12. I'm going to call that line 1. Here I will also solve for y. I'm going to try to do this in my head for space reasons. So y has to be greater than or equal to, let's see, it's going to be negative 2/9. So negative 2/9 x plus 4. That's line 2. And finally, here I can divide through by 3. So it's really like x plus y is greater than 8. So this is saying that y has to be greater than or equal to negative x plus 8. Okay, and let's call that L3. Okay, and now I'm going to graph these. I haven't done this problem in a while, so I sort of forget the exact scale that I need, but I'll figure it out. Let's see. line 1 is going to have y-intercept 12 and x-intercept, just got to think about this for a second, x is 18. I guess I need to go out to like maybe 18 or so. So maybe this is fine. 5, 10, 15, something like that. 5, 10, 15, hopefully that fits. I didn't think about it too much. Okay, let's go. The first line up here at 12 is the y-intercept, and the slope is -2. So that means we're going to hit down here at 6. I hope that's right. Yeah, when y is 0, x is 6. Okay, so that's my first line. I'll draw it in. That's my, looks a little sloppy, but could be worse. That's line L1. What's next? Now I graph line L2. Okay, now the y-intercept is 4, but maybe it's easier to just plot the x-intercept. The x-intercept when y is 0, x is 18. So that's when I'll go all the way over here to 18 and put a dot. This seems like the best bet. So this line over here is L2. And line L3 is -x plus 8. Okay, so that's going to be up here at 8. And the slope is -1. So we'll be also here at 8. So it's going to look something like this. Okay, so I put quite a lot of care into this graph. I'm almost positive that it's accurate, or accurate enough for what's going on here. And says me, if I need y to be greater than, then I need my output to be above line 1, I need my output to be above line 2, and I need my output to be above line 3. And also, of course, x and y have to be positive, which is why I only drew the first quadrant. It's kind of taken forever. So this point here is 0, 12. This point here is 18, 0. And it appears from my pretty accurate graph that what I have here, my region of feasibility, is in fact an infinite region. So it's not quite true that my region is going to be a polygon. There are cases in which it's sort of an infinite polygon, and this is one of those. But okay, this infinite region in quadrant 1 is my region of feasibility, and now it just suffices for me to find the ordered pair which minimizes the price per bag. Well, since the price goes up, of course, as x and y get bigger, then that means that I should want x and y to be as small as possible. And so for any point you pick, you're always going to do better by going down, because that will have a smaller y, and you're always going to do better by going left, because that will be a smaller x. And so we're looking for the sort of smallest x and y's that are possible. So 18,0 might be a solution, 0,12 might be a solution, and so might these two here be solutions. Okay, and so what I now need to do is solve for what this point is. I need to know the coordinates of this point. This is the intersection based on my notation of L1 and L3. So I'm going to solve for where L1 equals L3. Well, let's just do that right now because I'm running out of space. Let's see, I get -2x plus 12 equals -x plus 8. So that means that x is 4. So that looks pretty good. And when x is 4, y is 4. So I guess that's point, that doesn't seem right. But maybe it is. No, it's just can't be right. Yeah, I guess it is. When x is 4, y is 4. Okay, so that means my graph is pretty bad. But I guess that's the point 4, 4. Sorry, 1 second. I'm just kind of doubting myself. How could my graph be so wrong? Let's see. If I plug 4 in here, I do get 4, and when I plug 4 in here, I do get 4. So okay, I guess that's 4, 4. It just looks really bad. It just looks like 3, 6 or something. But anyway, never mind. What is this point that I also don't know? This intersection of L3 and L2. So L2 intersect L3. Well, alright, when is -2/9 x plus 4 going to be -x plus 8? Let me multiply through by 9 really quick. So I get negative 2x plus 36 equals negative 9x plus 72. I guess I wanted to do that. So this gives me 7x equals 36. So x is 36 sevenths. Is this really the right answer to this problem? I'm now doubting myself or something. Yeah, I think I did something wrong. What did I do wrong? I've made some kind of horrible algebra 1 mistake. What is it though? I can't find it. Let me just kind of try again or something. This is negative 2x plus 12. This is negative x plus 8. X is 4. And I am slowly, this video is falling apart a little bit. How, what have I done wrong? I think everything was good up until this point. Well, hopefully. Oh, I made a horrific, tiny typo a long time ago. 2 units of A, 2 units of B, 3 units of B, 1, 9, 3. Wait. 2x plus 12, 2x to 9, 2x. Because 2. What? Well, there is the entire problem. The entire problem is that way back at the very, very, very beginning, oh my gosh, that is the wrong number. Well, I'm not remaking this video because every single thing I said was quality explanation, but I just had one number up. I literally copied the problem wrong. In fact, brand X contains 2 units of nutritional element A, 2 units of B, and 2 units of C. So that makes this 2, which that suddenly must change everything somehow, because now this is this should be a 2 here. Ugh, this is terrible. Not re-recording this. So this is 2x plus 3y has to be greater than or equal to 24. So in fact, y is, oh my gosh, negative 2/3 x plus 8. And therefore this picture is also kind of wrong, but not horrifically wrong. It's still true that when x is 0, y is 8, but now when y is 0, x is 12. Okay, so let me just erase this. I'm really sorry. Mistakes happen. So this is 12 now. So now the picture is perhaps even more clear or something, but that's 12, 0. But anyway, that's outside my range now. So okay, catching back up to things, it's now this point and this point that I need, but now still trying to find the intersection of line L1 and L3, I don't use, I use now negative 2/3. Oh my god, negative 2/3 x plus 8. Okay, good. Now I need to solve this equation, and okay, let's do it. When I add 2 to negative 2/3, I get 4/3 x, and if I subtract 8, I get 4. So the 4's cancel, and in fact, x is 3. Okay, doing my algebra 1 this time correctly with the right numbers, I get that x is 3, and when x is 3, y is 6. And I'm just going to check that in both equations. Okay, so y is 6. Okay, so, sorry we wasted 3 or 4 minutes there, but in fact, this is the point 3, 6. Okay, great. Which makes this also wrong down here because I, once again, I had the wrong equation. So this is negative 2/9 x plus 4 equals, now I want this to say negative 2/3 x plus 8. Okay, multiplying through by 9 gives me negative 2x plus 36 equals, when I multiply that by 9 I get negative 6x plus 72. This is a hard problem, I guess. So this gives me 4x equals 36, and so x is 9. Okay. Finally now, if x is 9, y has to be 2. And I'm going to check that in both equations. Okay, well I caught my error because I was being very careful, but it would have been better if I had made no error at all. Here I get this point 9 comma 2. Okay, now by this sort of grand theory of linear programming, though my region of feasibility is infinite, there are only 4 possible numbers which could be solutions to my linear programming problem, because, as I mentioned, I can always do better by going down and to the left. So that shows the answer needs to be somewhere on the sort of the border of this infinite region. But then also, I could always probably do better by going up or down one of these lines. And so it suffices, therefore, to just test these 4 points. Okay, and now there's also a factor of 5 here in this p. This is really 5 times 5x plus 4y. So really what I need to do is I need to minimize 5x plus 4y. So the final step of this problem is to take the expression 5x plus 4y and see what its value is for these 4 numbers. So 0, 12, 3, 6, 9, 2, and 18, 0. And I'll plug all 4 of those in and see what I get. Okay, trying to be careful now. This is 48. This is 15, and 24 is 39. That's just true. 45 and 8 is 53. And 5 times 18 is 90. 50 and 40 is 90. Okay, and so this time I'm double checking the right answer to make sure I'm right. So, after all of this, I conclude that here's my winner. My winner is this one right here. Because what we're finally sort of computing in this chart is, well, one way to make these giant homemade bags of cattle feed is to use none of brand X, but 12 of brand Y. Well, if I do that, then I'm going to be spending $48, actually $48 times 48 times $5 to make one of these giant bags. Etc., etc. So the best option that also meets all these requirements is to use 3 bags of brand X and 6 bags of brand Y, and that meets all the requirements, but it gives me a cost of 39 times 5. And so the final answer, if we're going to write it out as a sentence, it's use 3 bags of X and 6 bags of Y, and put all of those 9 bags together in one giant new homemade bag. And by the way, that's going to cost you 5 times 39, so that's going to cost $195 per homemade bag. But you just can't do any better than that. That's the cheapest possible homemade bag that you can make. That also satisfies these constraints. So also meets the minimum nutrient requirements. Okay, good. Very long video, but hopefully now everyone knows how to do that problem. Goodbye.